Thank you. I just want to make sure everybody can hear me with the mask on. OK, great, great. OK, so I'm going to be talking about the role of materials and microstructures. Basically, microstructure makes up a system with different components within, say, an electrode. And then that requires us to consider different material properties in different parts of the structure. This is a kind of picture that you might kind of visualize what's happening. So what you see here is a cathode particle, where outside the cathode particles, active material. So this is the composite electrode, composite cathode part of it. And you have a cathode particle, but within that, there's actually concentration gradient of lithium. Transport has to happen in electrolyte phase, which is transparent here, but also has to happen within the particle as well. And all that has to be coupled with electrochemistry. So that's what I'm going to talk about today. And here's the lesson plan. So first, I'm going to give a bit of general information about material science and engineering, just because some of you are not from material science background. In fact, I'm motivated to do this because when I was finishing my PhD, I had no idea what material science and engineering was. I didn't know it existed. And then first time I heard the discipline's name, materials science, and then I said, that's grammatically wrong. So anyway, that's how ignorant I was, and I also now try to, fix my mistake and then try to, advertise this is actually a field. And then I'm going to get into the actual subject of electrochemistry, but I'm going to start focus on batteries because it's a very rich system. And then what goes into batteries, what kind of components there are, and then describe governing equations. And then that actually allows us to identify parameters that are needed to describe the process. So then I can talk about key material properties, how they are determined. And then I'm probably not going to get to this today, but how microstructure affects electrochemical dynamics. And then tomorrow, I'm going to say more about this, pick up from there. And then some simulation results to just give you the kind of idea of what kind of things you can actually study using simulations, and how stochasticity come into play. If my voice volume goes down, and if you can understand me, please raise your hand and let me know. And then we are going to also have a hands-on session on phase field modeling next week as well. So that's the red part is what I'm going to try to cover today. So material science and engineering is really focused on this relationship between processing, how you put things together, to what kind of structure you're going to get. And many people, even in material science, think of structure being like atomistic structure, how the atoms are arranged in crystals, for example. But actually, there is a big part of microstructures. Many materials have multiple components to it. Even in the kind of just structural materials that you think is a chunk of material, chunk of metal. If you take a slice of it, look at the under like microscope, you're going to see multiple phases. And those phases actually affect how materials behave. For example, how they deform when they're bent or like stretched. So that changes the properties. And you want to actually manipulate all this in order to get the performance you need in order to to make things lighter, make things better, make things work better in general. So, and then the way my group approach, and many of us here approach is a computational method. So material science and engineering, as mentioned, is developing the relationship between processing, structure, and property and performance. So often it's drawn or visualized in a tetrahedra like this. And each of these segments actually are governed by underlying physics. So, but, you know, like in physics, I came from physics background. You know, you could make pretty simple approximations. And that's, you know, sometimes you could solve things in the back of an envelope or maybe at least, you know, 5 pages of derivations. But that is not often possible in materials because it's quite complex. First thing that we have to do in studying materials is modeling to determine what physics or chemistry or other aspects of it we need to consider in studying the system. And that often leads to some kind of equations. In our case, usually comes in the form of partial differential equations. And then you then have to solve it. And it's hard enough that we have to use computers to solve that. So that's the simulation part of the computational material science and engineering. And that's the prediction based on the base of the model. So computational material science and engineering is the study of materials by modeling and simulation, combining these two things. So the way we start typically is to look at the physical phenomena. So that is usually experimental results. And then we start thinking about how do we describe this phenomena? And then, so that's kind of where our domain knowledge comes in. And then you can, depending on the problem, you can do classical dynamics, like molecular dynamics, or maybe you have to really worry about electronic structure, in which case you have to use quantum mechanical methods. Sometimes you have to apply statistical mechanics. And I think a lot of ways we take into account the stochasticity comes in method, it can be solved using a method that's developed in the statistical mechanical world. In the microstructure world, we have to keep track of interfaces. Where do the interfaces go as they evolve, or how what kind of effect it has on the surrounding. You can do this with something called sharp interface method, in which case you grid up the interface in a discrete way. And I mean, when we get to solve it, but it's a dividing surface that is infinitely thin, and you have to resolve it. In the another approach, it's called diffuse interface method. You assume that these regions occur over some finite thickness. It's often an approximation. It could be physical, but often it's an approximation. And but it allows us to solve the equation in a much simpler way. So when it gets back to once you have a physical model, you have to solve it. You have to come up with some kind of mathematical description. This diffuse interface actually helps us quite a bit. Mathematical description for other techniques also exists, but often in the type of modeling we do, we get partial differential equation with associated boundary conditions and initial conditions.
Ask a question?
Yes, of course.
So you're using the diffuse interface to make things a little bit easier.
Yep.
But in terms of the actual physical system, is it more likely to be diffuse or very sharp?
Depends on the system.
Okay.
So you can have a diffuse interface. For example, there is this phenomenon called spinodal decomposition. So if you have a mixed binary system, say, and it's at high temperature, it's solid solution because the free energy function looks like this. So it wants to be mixed. Now, if you quench it for, to a lower temperature, this free energy function can develop a double well where it wants to phase separate. And during that phase separation process, it's going to have, if you start in spinodal region where it's kind of like a bump, like here, what happens is that you have a diffuse interface, and it could remain diffuse depending on the parameter. But so like semi, not too quenched, then you'd have well-defined thickness of the interface.
Okay, so I guess what I'm asking is, what would you rather have, a diffuse interface or a sharp interface if you could do them equally well?
So, you mean numerically, to solve it numerically?
Well, no, I mean, you said the reason you like diffuse interface because it helps the numerics.
Yeah.
But then there's another problem is, well, fine, if you could do numerics or sharp interfaces, which way? Then it's a choice between what's better.
I prefer diffuse interface because you don't have to, for numerical reasons.
No, I know. But the point is, if that wasn't a
study,
concern, which is the one you would choose for modeling the systems you use?
Modeling the system.
I mean, the ones that you're typically interested in. Do they have diffuse interfaces? Or
They usually have a sharp interface because it's like solid surrounded by something else, and then there's not really diffuse interface. But you can show that when the interface, diffuse interface, artificial diffuse interface, is thin enough, it gives you the sharp interface equation. So yeah, but it's a numerical or mathematical method that allows us to solve the equation more easily. Not because it's physically diffuse. Yeah. And so you have this mathematical, once you have the mathematical description, and then this is actually where modeling comes in, because you can write a partial differential equation with every phenomena that you want, you could possibly have, right? And then that's going to be too expensive to solve. So some of the terms needs to be gotten rid of. And you can do that by some kind of dimensional analysis, do the back of the envelope calculation to see how big those terms are. And then you end up with the equation you want to solve. And once you have that, then you can actually solve it. You can solve it using finite difference method, which is probably the simplest to learn. You can also solve it using the finite element method, which we typically do. There are the methods that are available to solve those equations. So, and then once we go through all this process, you now can run a simulation because you got a code, which you can run and see what that's going to tell us. So in my group, we are interested in microstructure evolution, and we do a simulation for that. We also, we can get structures like this in the simulation, and it's rather complicated. So sometimes it's a matter of figuring out where the needle in the haystack, and so 3D characterization to figure out what's important is one of the things we do. And then we also develop some methods to study both in material sense. Phase crystal is one method that's diffuse interface-like mathematical approach, and it's variational method, just like the phase field model. But then it's atomistic level. Smooth boundary method I'm going to talk about because we use that quite exclusively in my group. So electrochemical phenomena that happens in batteries. It also happens in fuel cells. So we study solid oxide fuel cells and electrolysis cells. And then also corrosion, right? So if you look at all these equations, it's actually quite similar. So we've studied microgalvanic corrosion, for example, and developed phase-free model for these systems. More recently, we are studying actually corrosion in molten salt, which I think is quite different from aqueous solution corrosion. So it would be great to talk about this to collaborate with people here, because there are a lot of interesting ab initio molecular dynamics results coming out of my collaborators group, looking at the coordination numbers, and these are very interesting, right? But how does it change the reaction rate, corrosion rate? And they are not sure how to do that. So that'll be really interesting to do. And so I'm going to talk about batteries today, just to kind of focus on one thing. Yes?
Is molten salt like an ionic liquid?
Yes.
That's what I should think of.
Yes.
So you're doing this around all the time.
Yeah.
Well, that sounds like a ton of fun. Okay.
Yeah, but the more, but then ionic liquid often is like a organic, right?
Yeah.
These are like sodium and chlorine or potassium, usually eutectic, because they want to lower the temperature at which it melts.
Oh.
And then it's good for potentially good for nuclear reactors.
Yeah. Okay. Oh yeah.
So, yeah, if anybody is interested, let me know. I can tell you more. So here is the battery problem. The material properties at the atomic scale actually governs what happens at larger length scale. And eventually you got this, not just this microstructure, but you have to actually understand what happens at porous electrode level, right? So you have to somehow, coarse grain each level. You have to include this information in here, and include the information about what the particle does at the larger scale, and then try to understand or be able to predict what these electrodes, tens of thousands of particles, you cannot individually resolve it. So somehow we have to be able to take that into account, and there's going to be size distribution, there's going to be disconnection of conducting channel, all that stuff that are, key to make the battery actually work. So just a quick background and terminologies. So oxidation and reduction are the key reaction mechanism to make battery work. So redox is what happens. And there are electrodes. Electrodes can be cathode or anode, depending on the types of reaction. And actually, so when I say electrodes, it can be two things. I apologize. So for most, for lithium-ion batteries, rechargeable batteries, those electrodes are not single material. It's actually composite. So it can consist of multiple things, including active electrode particles, electrolyte, and electron conductor. It's a multifunctional electrode. And there are cathode and anode. So the cathode is where reduction occurs, and electrons are gained by a species. The anode is where oxidation happens, and electrons are lost by species. And electrolyte is this type of material where it conducts ions. That the ions can diffuse or migrate through it, but not electrons. Because if you have electrons moving around, then you're going to get short circuit. Separator is made solely of electrolyte, and it separates the anode and then the cathode. I'm sorry, there's a typo here. Anode and the cathode, this should have been cathode, to avoid short circuit. And I will correct it another time. So the simple batteries don't have this composite electrode. It's just usually metal. Here's a zinc anode with a copper cathode. And this is the electrolyte. You probably have seen or even played with potato batteries or lemon batteries, right? And these are actually providing, lemon and potatoes are providing this separator, okay? So, and it's got, in its liquid, it has ions. So simple batteries consists of anode and cathode, and then there's an electrolyte or separator in between. And the batteries can, devices that can store electrical energy in the form of chemical energy. So, it was a pain, right? I don't know, I guess most of you are probably young enough not to remember that, having to change like batteries, like, I mean, maybe even time to time now, but it's a pain. Isn't it nice now that you just have to plug it in and then you just wait for a little bit and it's pretty fast too, And so really the game changer here is intercalation compound. Intercalation compound have crystal structure that has kind of like a roomy area, like where lithium can come in and out relatively easily. When it comes in, it's only loosely bound, so you can take them out. And so you can discharge. So this is cathode case. So when it discharges, it gets lithium into it. And when you charge it, you actually put electric potential to get the lithium out of it to the other side of the battery, which is anode, usually made of graphite, another intercalation compound. And then to be ready for you to use the energy again. So, and then the important thing is that it doesn't change the crystal structure. The lithium just comes in and out. The crystal structure, host structure stays the same. That allows it to not degrade as you cycle it. So, and then the concept of chromic efficiency is used typically to describe how much energy it's going to keep as you charge and discharge. And the chromic efficiency is defined by the charge extracted to the charge you put in. So if it's lower than, significantly lower than 1, it's a problem, right? Because you lose every single time you charge and discharge and charge, you end up losing some portion of it. And even at 0.999, efficient of 0.999, which sounds amazing, right? If you do 1,000 cycles, and if you get the loss every single time, you're going to get less than 40%. That's why your good batteries goes bad after a couple of years because you do charge and discharge. The research type batteries, the ones that are being developed, they're way less than this. So, and then it's good Like it is, like 0.99 sounds pretty good, but it will degrade much, much faster. And then those are the challenges we have to overcome before that you commercialize rechargeable batteries. Yes?
But is swelling an issue? Is that one of the...
Swelling can be an issue, yes.
Has that been...
Yeah, so swelling is a big issue with solid-state batteries, especially. With liquid system, it is, but it's not as bad. But often in the liquid electrolyte batteries, the poor chromic efficiency comes from like SEI side reaction, SEI formation, and things like that. But yeah, the swelling is a big issue with solid state because it's kind of confined in the electrolyte, and then when the electrolyte gets, you have the cohesion, reaction gets, it's going to hard to react. You have fewer and fewer reactive area. Yes?
Do mechanical strain effects become an issue over time?
Especially in, I mean, it is for other materials too, but it's much worse in solid-state batteries. Solid-state batteries, just to be clear, it has solid electrolyte. So the whole thing is solid, which is great for safety reasons, but for the longevity, it's, it introduces a new aspects of it, that makes it difficult to keep, especially chromic efficiency and longevity to be a big challenge. Any other questions? Yes?
For these kinds of batteries, are there any alternatives that are being considered for lithium? Because I know lithium is pretty rare.
Yeah. So I think magnesium is one of them. But whenever you go up on a periodic table, there are two challenges. One is that atoms are kind of larger, right? So they get a bit sluggish in terms of like moving them around. So transport is really important in these systems, and the lower diffusivity is a big problem. Another problem is multivariant. Nature of some of those elements. So there's more of the chromic effect, and then that further reduces the mobility as well as sometimes reactivity. Any other questions? Okay. So here is a kind of schematic of rechargeable lithium-ion batteries. So it's called the lithium-ion batteries because you have a lithium ion that gets shuffled back and forth. And when it discharges, you have a lithium that's stored in anode, which is typically made of graphite. Lithium just kind of is in between the layers. And then the lithium comes out of the anode, gets transported to cathode side, and then this gets intercalated. The cathode gets intercalated. The cathode tends to be something like oxides, and sometimes other type of materials, but the oxides is quite typical. And then lithium ions react with electrons over here, and then it gets intercalated. So lithium ion comes here, and then electron comes here. So inside of here, reaction actually happens only in the surface, but you have to get the transport through, both for electrons and ions. So the reaction might look like this. This is for M being a metal, like manganese, cobalt, or nickel. And another side, you have lithium giving out electrons and becoming lithium ion. So, and then electrons actually travel outside of the circuit. I just want to point out, because there was I think it was something on the qualifier exam, and then somebody was asked, this person was working in a battery. None of my students I was asked where the electron goes, and couldn't answer. But the electron does go outside, or otherwise it's not going to light up your bulb, right? So that's how it works. And how does this happen? How does the lithium go from one side to another? And this is about the thermodynamics of the system. So lithium in anode is less happy than lithium in the cathode side, which is happy. So lithium has a lower chemical potential in the cathode than in anode. So it's like you have a hill, right? And that you put the ball over here, it's going to roll, right? So there's a driving force, just like a gravitational potential. Chemical potential actually gives you the push it needs. Okay, so yeah, lithium in the cathode is happier. And you can actually quantify those driving forces from the thermodynamics calculations, thermodynamics measurements, etc. So this is the example of a lithium ion phosphate. You can calculate what the chemical potential is and different phases, and then with respect to lithium, metal, and lithium in the graphite. Okay, and then so you have this much driving force to go from graphite to lithium ion phosphate. So the charging process, now you have to reverse this, right, process. So now you got, this is happy over here, lithium is happy over here. So you have to make it unhappy. So you use the electrostatic potential to raise, so it was like this, right? Now you're going to tilt it up over here so that it can roll this way. So voltage is applied to attract lithium and electron towards the anode. And so you cause a reaction to happen, this reverse reaction. Lithium ions diffuse and migrate through the electrolyte, and then electron moves through the here, driven by the applied potential, which causes the current. Usually it's constant current instead of constant voltage. And then this reaction happens over here, and then lithium intercalates into the graphite. Okay. So I had this picture. Happier. I also said happier. Why happier? Not happy. Why not that big smile? Anybody? Why would that be so bad if this was like really, really, really happy over here? What is it? Oh, catch on fire? No, it's actually, well, I mean, you can always, puncture this and then cause fire, but so other ideas?
It's reversible. It's reversible, so.
Yeah. So you want to be able to put not too much energy to get it out, right? So if this is so happy over here, really low energy, which means that it would be more bound, right? It's more stable, more bound. To break that bond, you'd have to put a lot of energy to get it out, and you don't. You want to do this as energy efficiently as possible to get the lithium from here to there. So it's really an intricate balance, right? You want to make sure that lithium wants to go from here to here when you are using it and you get enough voltage, right, for the device. But you don't want it to be so big that you can't get it back that way. Okay, so a quick review and question break. So I've talked about general information and terminologies, oxidation reaction, oxidation and reduction reactions, electrodes, the two different electrodes corresponding to those. Oh yeah, I probably just, another thing I wanted to make sure I forgot. When you like positive versus negative electrode, you want to think about just here, right? And another thing I forgot to tell you is that by the definition, that the chemistry, electrochemistry definition, the reduction happens in cathode, right? But when you're charging, it's actually reversed, right? But we don't actually start calling this one anode at that point because that's too confusing, right? So we just stick with the discharge terminology. And during discharge, this is cathode. And we are just going to, and this is anode. We are going to stick with it. And then which is positive and negative. If you get confused, make sure you look here and then look at the charge of electrons and which one it should be. Okay, so that was that. And then electrolyte is electrochemically inert and then transports ions. Some simple batteries I talked about, and then focus more on rechargeable batteries. So any questions, any remaining questions? Yes. Oh, yes, sorry. Go ahead, and then we'll come back.
So the voltage that you see in the battery, that's set by removing one electron from the lithium. But you say it's not super happy, so I mean, the happiest it could be is that the energy difference is a full volt. So it's really, somehow it's partially solvated charged when it's in the cathode then. And that's, I guess I don't see why it wouldn't be optimal to have it super as happy as possible. Why? So I'm putting the energy back in, but I want to put in as much energy. I want to get as much bang for one electron as I can, right?
It's true if you don't need to recharge.
Yeah. Okay.
When you recharge, you have to get it out.
That's the energy company. That's whatever, California Energy, whatever. That's their problem.
Yeah. So high voltage batteries have exactly that. It's higher in
it's
deeper
higher.
in energy.
It's higher work to charge.
Yeah.
But then I'm getting more energy density.
Yes.
Right?
Yes. It's true.
Why wouldn't I?
Inefficient to charge a battery. If it's a high voltage battery, is the efficiency of like the
High voltage batteries, you have to put a lot more voltage in order to get it back, recharge the system. And the problem is this. So when you start putting higher voltage, there are other material aspects that you have to consider because
destroy the battery.
Electrolytes become unstable. There's going to be more side reactions. The material itself can start losing. So those are oxide, right? They can start lose oxygen. So there are many things that can happen. So yeah. And so the rule is like, basically, what's the ideal voltage you need for specific purpose, and then go from there. So some materials are better for high voltage, some materials better for some other applications. Any other questions? Yeah, oh yeah, that's right, I'm sorry.
So we have an anode material, a cathode material. We have the electrolyte as well as a separator.
Yeah, so separator can be just a gel with the same electrolyte.
Okay.
Yeah.
And so the separator is to prevent the lithium ions from going to the cathode.
The separator needs to it's electrolyte, so it needs to transport ions, the lithium ions. So lithium ion needs to go there, but you don't want the electron to go through because you want to force the electron to go this way, right? So that's why it's separate. It's separating electrically. Yeah. Is that clear? Okay, great. Okay, yep.
So for getting a battery with good performance, it's been getting at it, but what's the major trade-off, and is there any kind of equivalent to Moore's law or anything about the efficiency, performance of these batteries?
That's a good question. I haven't thought about it, so I don't think I can quickly give you the answer, but I can look into it.
I mean, there is a thing, if you want more voltage, you just put them in series.
Yeah,
so that's easy to do.
That's
So
true.
you don't have to redesign a single cell.
That's right. That's true. That's true. Yep.
Is the separator a mature technology, or is that still something that people are?
Electrolyte, people still develop the electrolytes. So there's a lot of actually.
The cathode electrode.
There's like work in all areas, and so like electrolyte, especially there's some efforts as to like autonomous experiments because there's a composition access for like, so you have the solvent, and there are many different solvents, and then there are ions that you put, the supporting ions that you put in there, and then like phosphate. I get confused with the phosphate ion maybe. And things like that. Different kind of ions that you can put for the anion part, and then you have the concentration of it, the range of concentrations. So there's a kind of a large parameter space, and so there's been some work on like kind of autonomously kind of explore parameter space in that area. So yeah, I think there's a lot of work in all around cathode, electrolyte, and then those are just in liquid, right? Liquid systems. So, and even like the composite electrode, how much conducting material should you put? How much binder you should put? To keep the mechanical stability too, right? So there's a lot of not just the material that you put in there, but also how much and how to construct the electrode. And the anode too, so how much you calendar, etc. So, okay.
Excuse me?
Yes.
So the
I'm sorry.
separator, okay, like the lithium ion parts. So what is the relation with the dendrites?
Yeah, so separator, you don't want the dendrites to go through.
Yeah, so it's like...
Yeah, so because once the dendrite goes through, you have electrical conductivity, right? So so sometimes they put something called a Silgard, which is like a more stiff material to prevent the dendrite to penetrate if it does happen. I should probably learn more about manufacturing processes, but so the separator could include these kind of stiff component, but still allowing lithium-ion conductivity.
So, but is there a compromise that one should find between, extent of the electrolyte phase and closeness of the? So, how far should the separator be?
Yeah. So for the energy density, mass, volumetric, and mass, it's better to make it thinner. But if it's too thin, I think Samsung had a problem, right? Like batteries, they had a lot of fire or short circuiting.
You can like use up the electrolyte also.
Yeah, that's
too
true.
little,
Yeah, that's true. Yeah, but they push it too far. Actually, this is recorded, so maybe I shouldn't have said. But yeah, but I've heard like in the manufacturing they push it too far to reduce the mass of the cell, and then have issues, resulting from that. So there's definitely, the trade-offs: safety, longevity, and the initial performance. Yeah, I'm not an expert on that, but yeah.
Distance between the cathode and anode important from like a migration perspective?
How thin? I think it varies. Like laboratory scale ones are different from the manufactured ones, and I do have one picture there, and I don't remember how thick the electrolyte. If I come across, I try to point out.
Is there a trade-off in the kinetics of the ions?
Yeah, it can. Electrolyte, I'm going to point out later on, but electrolyte tends to have a high diffusivity, liquid electrolyte especially. But where it can have problem is usually in the electrode itself, where there's a high tortuosity. So, but it can be. If it's too thick, obviously, it's like a diffusion length, increases. The length over which it needs to be, lithium needs to transport increases. Any other questions? Okay. So what I'm going to do now is talk about the continuum modeling. So, we saw the atomistic pictures and electronic structure calculations, etc. But here, we don't want to worry where the atoms are. We don't want to worry where the electrons are individually, right? Just like thinking about concentration to coarse grain order, or electrons, just look at the current. So the driving force for chemical transport can be described by the in terms of the chemical potential. And the driving force itself is proportional to the gradient in chemical potential. So how it changes in in space, and basically d chemical potential dx, where x is the position. And then depending on the cathode material, system can be a single phase material or multi-phase material. So just like I already talked about spinel decomposition, at higher temperature, it could be single phase. So the free energy looks like this, and chemical potential is just the slope of this free energy function. But then, when you at the low temperature, you can have a double well like this. And the different materials just intrinsically have kind of single phase like behavior by the thermodynamics of the material, or phase separating behavior. If it's single phase, you can just use diffusion equation to describe whether how the concentration evolve. If it's multi-phase, then we have to use something called phase field equation. But it basically is a generalized diffusion equation where the driving force is written in terms of the chemical potential. And these transport equations, along with the current continuity equation, are coupled by the reaction rate at the surface. And Richard talked about Butler-Bowman equation, so that's exactly that, the typical one that people use. And so what does it look like at the end? So you have active electrode, and then here's the electrolyte. So lithium diffusion and phase transformation in the solid, depending on it's single phase or not. And then lithium ion transport in the liquid. And then the current continuity in the solid and the electrolyte. So current has to basically charge conservation. And then the reaction rate at the solid liquid interface. So that's a big picture, right? And then you input actually numbers or the symbols. So diffusion equation looks like this. Hopefully, most people are familiar with what diffusion equation looks like and what it comes from. I do want to tell you that the generalized version of that is you write flux as a function of the gradient of chemical potential. M tells you how easy the species respond to the driving force. Negative comes from the fact that it goes down the hill, right? And then mass conservation equation is just given by what comes in versus what goes out, which is given by this minus divergence of the flux, right? Like this. And by combining, you minus and minus cancels out, you get grad dot m grad mu. So it's just like this, but replacing diffusivity with mobility and the concentration with the chemical potential. And that would actually model either cases because it's generalized. It knows, chemical potential knows that that's the free energy of the system. And then the current continuity here. This is the concentration. This is also for ion, lithium ion in the electrolyte, and then it comes out of the mass conservation equation, just like this. But it includes the fact that the lithium in the electrolyte is an ion. It's got a charge, so you have to take into account that there's a migration term.
Is there a tendency for the interface to become unstable?
So it depends, but usually not in the intercalation material, because this whole structure stays the same.
So you don't get fingering of
right.
fluids people would think.
However, if you're talking about the lithium metal anode in the electrolyte, it does grow dendrites. Yeah. Okay, so traditional model batteries, there are a lot of assumptions that goes into it, but often, for the most part, microstructure is ignored or assumed that the concentration is uniform along that line, right? So there's a lot of assumptions. One better assumption would be something called a shrinking core. So as the lithium comes in and out, there's a core, one phase, and then, those are two different extremes, right? Assuming constant concentration means that you have a very fast transport, diffusion in the particle. This would be for like two-phase material, right? So, or maybe slow diffusivity. Okay, so, but real microstructures are very complex. And oh no, there's no scale bar. So this is a separator here. I was going to look up how thick this was, but no, I don't have the scale bar. So I have to look it up in the original reference, and then I'll let you know. But here is the cathode. Here, from here to here, it's graphite. And here is like a separator, electrolyte. phase. Okay, so if you just like do 3D characterization of these, this is from my collaborator Scott Barnett's group. They actually can reconstruct what these things look like. What can be noted here is that the lithium-ion transport path inside of the composite electrode is very complex. It's torturous. So maybe this one has scale by 50 microns. Okay, so like maybe like 30 microns, something like that. Okay, and then that's supposedly from a laptop battery. So so you can construct this microstructure. And then, but now the question is, how do we even simulate with this, right? This is so complex. So I'm just going to tell you about the another type of diffuse interface method. This is not material specific, that this is just how to set boundary conditions. Because remember, we have one set of PDE to solve here, another set of PDE to solve here, and then you have to couple it with the boundary condition, right? So how do we set the boundary conditions? What we developed is something called the extended smooth boundary method. And there was a smooth boundary method that was suggested by Bueno, Orovio, and others. And it was for no flux boundary conditions only. And they just wrote down the equation. And they didn't say why it worked. They just showed that it worked. So, so we tried to understand the method and then try to generalize it by understanding the method. So, and it's actually simple. You can just, I mean, if I knew what I needed to do, like what I wanted to come up with, actually, all the math I needed to know to do this was just college level calculus class. So let's start with the diffusion equation, because everybody knows diffusion equation. I forgot to mention, I'm going to use something just like a phase field model, phase field order parameter, but just indicates inside of the domain and outside of the domain. That's what I want to do. And have something smooth to transition between the outside and inside. So inside it's 1, outside it's 0. And you can reverse this, right? So if you do 1 minus this, now you can just get all the outside, right? So for the inside problem, I multiply with this window function psi, and I distribute it. And then I want to get some kind of signature for the boundary, which means you need a gradient of the psi, right? This window function. But you can just stick it in. You have to apply product rule of differentiation, which you learned in college, right? So you got that expression. And you note that this psi and that psi, 1 is 1, right, inside where you want to solve the equation. And then this is 0 inside. So you get, this goes away, and then this is 1, and you recover the original equation. So that's all there is to it. And OK, now what do? You got this thing. This is non-zero only on the boundary. Then if you want to set Neumann boundary condition, which is Grazzi, right? You can just set what you want, boundary condition value. In fact, this is just the negative, the minus here times this. It's flux, so you just have to put the reaction rate right in there, and you're done. OK. And you can just use finite indifference method everywhere, but that's, you have the boundary condition set inside of the domain. So you can do simulation, oops, sorry. You can do simulations. Just give you some idea of what it looks like. You can do charge, discharge, right? Now it's discharging, and then charging. And then you have a whole bunch of different parameters that goes into these models, and I'm going to talk about it later on. But what's interesting that we saw here, yes?
So is the precise smooth? Is the function precise smooth? Is the function precise smooth?
It's smooth, yeah.
So you say its gradient is not zero only on the boundary.
Yeah. There's a certain thickness to it. But because this function goes from 0 to 1, you integrate across the normal direction of the interface. You actually integrate to be the right amount. Because like, kind of like you integrate it, so you do the Gauss's theorem kind of thing, and then you get 1 minus 0. So.
Is it discretely conservative? I mean, is it discretely conservative? I mean, that's what,
discretely conservative, does it depend on how you discretize it?
Well, what I mean is that if you did a problem, are you losing whatever it is that's diffusing in or out, or do you conserve the mass?
We haven't had any issues. We do check it.
It may not be zero. The conservation may not be exact, but it's close enough.
Yeah.
Because there's some methods where you get exact numerical precision.
It might be, it depends on discretization method.
No, that's the point. It can't be discretized in a conservative way. That's an issue. Yeah, I don't know. Maybe. That's no idea.
Yeah, we get very good conservation. Let's see. Did we talk about this? Yeah, so what we saw, this system is actually single phase material, at least in this concentration range. We are seeing something that looks like shrinking core, and that's only because of this diffusivity change as a function of the concentration. It just dives in once it gets to certain concentration, and it really slows down. And then you get this like shrinking core-like thing. And then that means that this interpretation of the thermodynamics from experiments actually has to be done quite carefully. So, okay, maybe I should keep going. Another thing we found that was interesting is that actually we saw gradient in the concentration of lithium ions in electrolyte, even on over pretty short length scale here. And that is attributed to this complex microstructure in this system. And then usually it is all complex, right? They try to pack as much active material into the volume. And as a result, you end up getting very tortuous path. So, so you can't assume that lithium ion concentration is constant throughout the electrode because of this tortuous path. And if you don't do that, you're going to get some wrong. If you assume otherwise, then you're going to get wrong answers. So actually, model must take this tortuosity of the system into account, even though the diffusivity surface is really, really large. It's still going to be a problem. And using those kind of, once you have the model, you can do a lot of different things. You can charge and discharge, like kind of like a numerical experiment at a different rate. Look at the hysteresis during charge and discharge, in a cycle, etc. So you can do those kind of simulations. So what kind of things you can do with the model? So this is a virtual discharge cycling. How do microstructure affect the rate? So you can tweak the microstructure, see what happens, how much stress results during the cycle, how can we reduce it, what kind of materials will perform better. Maybe we should look at different parameters and what parameters actually is limiting in this case. And if there are new theories or expressions or values for material parameters, how does it affect overall performance of the device? And I think this is a key question, key factor that, like I hope that we can actually help this community because, we are going to be developing new description of interfacial mechanism. So how does that then change the overall battery behavior and performance? Okay. Okay, so quick review and question. Just, okay, we talked about governing equations, differential equations. I don't know, that's right. Different equations must be solved in different material phases. Based on the mass conservation, those equations are based on mass conservation and current continuity, coupled reaction rate. Yeah, so any questions? Yep.
On the previous slides, in the materials parameters, so I presume that's the diffusion coefficient or mobility as a function of concentration, temperature, probably, maybe stress.
Yeah, actually.
Do you get those from experiments?
Yeah. That's the next thing. Okay, so that was the whole motivation of, because I wanted to get to this, but I wanted to be concrete, right? I wanted to be concrete as to like why these parameters are important. And so we have this equation. Those are all the parameters that needs to come out from somewhere, right? So, so the open circuit voltage that gives us something about the thermodynamic behavior of the materials. Ionic diffusivity and conductivity, electron conductivity, exchange current density that goes into Vatrov-Volmer equation, transference number, etc. So all these things needs to come from somewhere. So, and then, they go into input. In some cases, you do need the stress? Yeah, elastic homologous and misfit and things like that, especially for phase separating materials. And the microstructure can be important. And some things can be obtained, and I'm going to talk about from experiment. But often there are some parameters that we don't have access to. So there may be some parameter optimization process that needs to be happening. So yeah, we talked about this. And here there were a number of input parameters, diffusivity. Oh, this lithium cobalt oxide is a well-studied system. So we actually had access to, for entertainment movie. I don't know if it's doing or not. Okay, yeah, it is moving. Okay, so this system is very studied. So there was some experimental input, and then these are the references. But in general, how do we measure them? So open circuit voltage is one of the easier thing. So charge and discharge a battery, ideally very, very slowly, so that kinetic factor is not influencing the the voltage of the system. So C/30, something like that, is the best. It takes a long time, right? That means that you actually, I forgot to mention what C/30 means. C/30 means charge or discharge over 30 hours. So it's a long time, right? So for the experimenters to actually run something like that, it takes a long time. So that's open circuit voltage, so the measure of thermodynamics. The diffusivity in active materials are obtained usually use a potential static intermittent titration technique or electrochemical impedance spectroscopy, and then you fit a model to it. And then, but what we find is that the data from PIT and EIS are often quite different. So that actually gives us a range to start with, right? And then we have to see what we think is more right. And then exchange current density is obtained by potential sweep to get the IV curve, current and voltage relationship. And then you get, that gives you a Tafel plot, something Tafel plot. And then you extrapolate to the equilibrium potential. And then that's the I naught. But the challenge is that you have to make that into something like per unit area. And the unit area that we need, that the quantity we need, is not electrode surface area. We, the nominal one, which is like, the area of the cell, right? We actually need it per area of the active working electrode surface area. And if you know how much there is, how much surface there is in the electrode, it's a problem because you can't, like we don't know like how much of the electrode is actually working, right? So yeah, that's a challenge. So there's usually big error there. And then conductivity is just IV curve on an individual component. But sometimes those quantity can be obtained using lower scale, like atomistic simulations. And I'm going to pick it up from here tomorrow, since my time is up. So I have 3 minutes to answer any other questions you may have.